Example 3, analyzing a graph. This time we're going to do it of a rational function, or a function that's a fraction. It says, analyze and sketch the graph of the function f of x equals x squared over x minus 1. The first question, or the first part when we're doing this, is we always analyze the original function. So remember, with rational functions, we can actually determine more information. So for the domain, you always set the original denominator. You say that can't equal 0 because we can't divide by 0 in any fraction. Add 1 to both sides, we would have x cannot equal 1. So thinking about a number line here, here's the number 1. You cannot be the number 1, but you could be every other number. So what would the domain of this function be? It would be negative infinity to 1, and then 1 to infinity. This is really important for us to notice is we are probably going to get, when we set the first derivative equal to 0 and the second derivative equal to 0, we should get 1 is a critical value or a possible inflection point. But because it's not in the domain of the original function, we can't plug in 1. That means it can't be a max, min, or an inflection point. So we are going to split up our intervals for the first derivative and the second derivative at 1, which you'll see as we go through the problems. But just remember, 1 is not part of the domain, so 1 could never be a maximum, minimum, or an inflection point. It's not even a point. All right, let's go on. So the next thing you want to do after you've done domain is you always want to see if you could factor and simplify your rational function. My rational function is already simplified. There's nothing that I can simplify any further. So now I can move on. But always make sure you simplify first. I'll make a little note here. Simplify after you've found the domain, but this one's already simplified, so we don't need to do that. Okay, so now how do we find x-intercepts? After you've simplified, what you do is you set the numerator equal to 0. Will give you your x-intercepts. Taking the square root of both sides, positive and negative is irrelevant in this point. We get x equals 0. Okay, so if I set the numerator equal to 0, which is really setting the function equal to 0, I get x equals 0. So that means that my x-intercept, again, an x-intercept occurs when y equals 0 or the function equals 0. So my x value is 0 and my y value is 0. If you note, that also gives me a y-intercept, but let's see what figure we get here. So a y-intercept occurs when x equals 0. And the x-intercept occurs when the numerator equals 0. So the y-intercept, I'm going to plug in 0. I'd have 0 squared over 0 minus 1. So that'd be 0 over negative 1, which is 0. So that tells me my y-intercept is also the point 0, 0. Horizontal asymptotes, we note and we look at this, notice that this function right here is top heavy. The degree in the numerator is bigger than the degree in the denominator. And because the function is top heavy, there is no horizontal asymptote. Remember, if it's balanced, it's the ratio of the leading coefficients. And if it's bottom heavy, it would have been y equals 0. But this is top heavy, so there's no horizontal asymptotes. That means my end behavior is going to go to infinity or negative infinity. We can find those vertical asymptotes. To find those vertical asymptotes, all you do is set the denominator. Once again, you have to simplify it first, but after you've simplified it, you set the denominator equal to 0. And if you set the denominator equal to 0 here, x equals 1, x minus 1 equals 0, you get x equals 1. So not only is that a point where it's discontinuous, it is actually a vertical asymptote. Remember, when you write vertical asymptotes, you do need to write the equation of the line, so it does need to be written as x equals 1, not just the number 1. You do need the x equals there. Okay, so let's continue on. What we need to do now is analyze the derivative. We've analyzed the original function, so let's analyze the derivative. Well, if you notice, this is a rational function, and with rational functions, when we have a fraction, we need to use the quotient rule. Unfortunately, there is no easy way to find this, any tricks of like separating and simplifying in this exact case, but let's go ahead and write down the original function for reference. It's x squared over x minus 1. And if you remember the quotient rule here, the quotient rule is low d high minus high d low over what's below squared, or bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So let's go ahead and use the quotient rule now. Again, it's the bottom, which is x minus 1, times the derivative of the top, which would be 2x, minus the top, which is x squared, times the derivative of the bottom, which is quite simply 1, all over the bottom squared. So that'd be x minus 1 quantity squared. Let's go ahead and do some simplification for this derivative. I'm going to distribute the 2x. I'd have 2x squared minus 2x. I'm going to distribute that negative. I'd have minus x squared. This is all over x minus 1 quantity squared. Again, I'm going to simplify that 2x squared minus x squared. It looks like my derivative, I'm getting, well, what would that be? X squared minus 2x all over x minus 1 squared. I'm even going to go one step further. I'm going to factor to see if it could cancel at all. I know it can't, but I can see that in the numerator an x is in common. And remember, the factored form is the easiest form to use when you are going to do a sign chart. So x times x minus 2, if I factor out the x, all over x minus 1 squared. All right, this is our derivative. The simplified form of the derivative, or we even have the factored form of the derivative. We need to find those critical values. And to find those critical values, you have to look, where's the derivative equal to 0? And where's that derivative undefined? The derivative is equal to 0 when it's a fraction, when the numerator is equal to 0. I'm going to use the factored form because that's going to really quickly get me to my answers here. I have x equals 0. X minus 2 equals 0 gives me x equals 2. Both of these are critical values. And I want you to notice that these values right here, these critical values are in the domain of the original function. So these are potential extrema, local maxes and mins. Let's go, where's this derivative undefined? The derivative is undefined when the denominator equals 0. Any fraction is undefined when the denominator equals 0. Square root both sides, you'd have x minus 1 equals 0, add 1 to both sides, and you'd have x equals 1. Again, this is not a critical value, and the only reason it's not a critical value is because it's not in the domain of our original function. So we still need to break it up at x equals 1, but x equals 1 cannot be a max, a min, or an inflection point. That's very important to notice. So let's go ahead and draw our number line, breaking it up at these 3 points that we have. Looks like we have 0, 1, and 2 if we put them in order. I'm going to go to f prime of x, and I'm going to note at 0, f prime of x is 0, and at 2, f prime of x is 0, and at 1, it's undefined. And that reminds me, helps me remember that. I cannot make that a max or a min. So my first interval is negative infinity to 0. I have an interval from 0 to 1, one from 1 to 2, and another interval from 2 to infinity. I need to test those numbers, one number from each interval. I'm going to be plugging that into, again, my favorite to plug it into is the factored form. X times x minus 2 over x minus 1 squared. I'm plugging it into that first derivative. Let's just check some numbers. How about negative 10? How about 0.5 would work for the second interval. How about 1.5 for the third interval, and I don't know, 10 for the third interval. It truly doesn't matter what numbers you pick as long as they are in those intervals. And I'm going to think about the sign. If I plug in a negative 10, the first part would be negative. Negative 10 minus 2 is also negative. And then the bottom, no matter what the bottom is, because it's squared, has to be positive. A negative times a negative over a positive is indeed positive. Plug in 0.5, my first factor is positive. My second factor, 0.5 minus 2, is negative. Bottom is always positive. Positive times a negative over a positive would be negative. 1.5, I'd have positive. That second factor is still negative. And on bottom, again, always positive. Positive times a negative over a positive is, again, negative. Plug in a 10, I'd have a positive times a positive all over a positive, which is positive. So marking this on my table, my derivative in the first interval is positive. Second interval is negative. Third interval is negative, fourth interval is positive. So what does that mean about my original function? Anywhere where it was positive, that means my function's increasing. Anywhere it's negative, it was decreasing. First derivative test says where it changes from positive to negative, I must have a maximum. And where it changes from decreasing to increasing or negative to positive, that must be a minimum. Again, a maximum or a minimum is an ordered pair, so I actually need to plug those values 0 and 2 into my original function. So let's do that right now. F of 0 I've already done. That was how I found my y-intercept, so we know that that's 0. So we know now that the point 0, 0 is a maximum. Let's plug in 2. We know this is going to be a minimum. So I have 2 squared over 2 minus 1. I'm getting 4. So that tells me the point 2,4 is a minimum. So let's mark down all of that. Anywhere the derivative was positive, it was increasing. That was the intervals negative infinity to 0 and also 2 to infinity. Anywhere the derivative was negative, it was decreasing. That was the interval 0 to 1 and also 1 to 2. Again, we cannot include the number 1 here because the function's not defined there. So you cannot say the interval 0 to 2. You do need to break it up at 1. We did have a maximum at the point 0, 0, and we had a minimum at the point 2, 4. So that's the derivative of the function. I want to remind us what the derivative of the function was. When we found the derivative, here's the version that we're going to be using to analyze the second derivative. So on the next page, the first thing I'm going to do is rewrite the original function and the derivative of the function. Then I'm going to analyze the second derivative and continue the process.